Thank you. All right. So yeah, what was I saying? So just to repeat, if somebody wants to go through the recording, um, till now what we had seen was that the address space of the process was put together, and even though different processes could be put at different places, and there was a lot of free space between the stack and the heap inside the process address space, and since it is put together, this would cause the free space to go wasted. It cannot be allotted to any other process, and that is called internal fragmentation. And another problem is that we assume the memory to be much larger than the address space. But what if the memory is smaller than the address space? So these are the problems that we'll discuss. So what we are going to see is how to support large address spaces. And the answer is going to be the idea of segmentation. And one basic idea is going to be that instead of having one pair of base and bounds registers per process, have one base and bounds pair for every logical segment of the process. Okay, processes address space. Okay, and what is a segment? Segment is just a contiguous portion of some particular length. Okay. Now, as we had seen, there are three logical partitions that we could divide our address space into. So, what are the three logical partitions? Code, heap, and stack, right? So, now what this will allow, segmentation will allow to put these things in different parts of the memory, right? So, and now since they are kept in different parts of the memory, the in between space will not be wasted. They will occupy only as much size as their uh, as much they have grown till now. So this will lead to less memory wastage. Okay. So for example, suppose let's go to our canonical picture of the address space. So let's say that address space was 16 KB. And this was, suppose the process or the code was sitting here from 0 KB to 2 KB. Suppose the heap started at 4 KB and it goes till 7 KB, let's say. So this is, and the stack was from 14 to 16. Oops. And the stack was from, let's say, 14 to 16. So this was heap, this was stack, and the remaining is free. This is free. So let's assume that the pink things are free. So this is what the thing is, and how we would want to put it, let's say, is suppose the OS wants to put it now in its memory. So suppose the OS takes the first 16 KB of the memory. So let's say the memory is 64 KB. So first 16 is taken by the OS. Then let's say, so this is halfway. This is 32 KB. At 32 KB, the code comes, and at 34 KB, the heap comes. It takes, so this goes from 34 to 37. Right. And let's say the stack was somewhere here at 28 KB. This is 26 KB. And now this space is free. Okay. So this is how the OS might now put the code heap and stack in the memory. Right. So, and now it will have these three um, pairs of base and bounds register. So bounds register last time we saw will contain the size. So the memory management unit will contain three base and bounds pair for this process. And what are they going to contain? Segment, base, size, and the code is going to start from 32 KB, and the size is going to be 2 KB. The heap is going to start at 34, and its size is going to be 3 KB, and the stack is starting at 32, sorry, 28, and its size is going to be 2. Okay, so the stack, again, the heap will go in this direction, the stack will go in that direction, and so on. Okay, so this is like the basic view of how the segmentation will work, and it will just take the process address space, and the free space will not be wasted because it will be allotted at different places, and the logical segments will have only as much size as they have grown till now.
So the base register for stack will be 26 KB, 28 KB.
So stack goes upward. So it will be 28. We'll see how these things will be implemented in a moment.
Okay.
So since the stack grows upward, we'll keep it at the bottom. Like, okay. Actually, it's going to be like 1 byte above the 28, but like for our purposes, let's consider 28. So base and bounds register, like they store the values exactly as previously. Right? And like base will have start of segment and bounds will have size. right? Just to like to check legality of memory access. Okay. So, for example, let's say a virtual address comes of 100. Okay. So memory reference to virtual address 100. So this is going to be, so 100 is will be where it is going to be in the code segment. So now what is the base of the code segment? So 100 is going to be the offset. So this is the offset, and now we'll add the offset to the base address. So 32 KB. So physical address base plus offset 32 KB plus 100 is equal to 32,768 plus 100. So this is going to be the physical address at which this is going to happen. Also, the hardware will check whether 100 is less than the bounds register. The offset is less than. So again, okay, let me write offset here just to be clear. Bounds, and it was so that it is less than or equal to the bounds, so it will make keep it legal. So the fetch will be performed. Okay, so suppose now another example. Let's take of the heap. So suppose memory reference to address 4200 of the heap. Okay, so if you see 4200 will come somewhere here, right? Okay, so now the thing is that if you add directly to the heap's address, so heap, if you see, is at 34 KB. But if you add directly to the heap's address, this 4200, you'll come outside. I mean, that's not what you should be doing, right? So there, the offset needs to be calculated a bit more carefully in this case. You should not be like adding directly to the virtual address directly to the base address of the heap in this case. So what do we need to do? So first we subtract the start of the heap's address space. So what is the heap's address space? Heap's address space is here, 4 KB to 7 KB in the virtual memory of the process, in the address space of the process. And what we'll subtract? We'll subtract the start so that we can get this offset that we actually need, because that's what will be going from 34 down to get to the exact physical address, right? So what is the heap's start of heap's address space? It's 4 KB, right? So offset. So this is called extracting the offset. Is going to do 4200 minus 4 KB, which is 4096. So this is going to be 104. Okay. So this is the new offset. And now the physical address will be calculated like before. This is, what was it, 34, right? Sorry. 34K plus 104 and whatever this value is going to be, 34816, let's say. Okay, good. And then again, if the address was illegal, then if the bounds register tells that, okay, whatever offset you have calculated is not like, within bounds, then it will issue a segmentation fault. Okay. So you would have seen this term many times while running C programs. So at least what they are for when you try to access them. I mean, even for some other things, it just throws segmentation fault, but at least where the term came from, now you know that. Okay, so these were two basic examples, but now there is a big question is that, okay, I said that for code, it is doing something different. It just adds the mm, offset to the base of the segment. For the heap, it first subtracts the start of the heap's address space from the uh, whatever virtual address has been generated, and then finds the offset by doing that, and then adds the offset to the base. So the question is that how does the hardware know which segment is being referred? Okay. Okay. And so why does the hardware need to know? Because as I said, different operations are needed for different segments. So one approach is called the explicit approach. Where the address itself will contain information about which the part of or which segment of the address space it refers to. So encode 3 segments in address itself. Okay. And how many bits it's going to take? 2 bits, right? In 1 bit, you cannot encode 3 segments. So here we had the process space to be address space to be 16 KB. So 16 KB is 14 bits. So let's say that we encode the segment into the top 2 bits of the address. Okay. So let's say that 0, 0 is code, 0, 1 is heap, and 1, 1 is stack. So if this was the address, so this is this was the 14th. Sorry. So we start from 0 and we go to 13. So these bits will, yeah, any question? So this will be the offset. Yeah.
The address size is 14 bits or 16 bits.
Here we are going for 14 bits because for 16 KB, it's like 1 KB is going to be 10 bits and then 16 times that, which is 2 to the 4. I mean, it can be 16 bit for something else, but then it would be
But
16 bit.
okay, got it.
We are just taking a like toy example where it's 16 KB.
Okay, yeah.
Okay. So the first 2 bits are going to encode the segment, and the remaining 12 bits are going to, from 0 to 11, they are going to encode the offset, or they are going to have the offset. Okay. Good. So let's see this also with an example that we had earlier. So let's take the heap example. So there was a memory reference. 4200, right? So if you write 4200 in binary, it's going to be the following. Okay, let me make first 14 bits 4, 5, 6, 7, 10, 12, 13. Okay, good. So it's going to be 0, 1, zeros, then 1, 1, 0, 1. Okay. So because 4200 is okay, so this is going to be, as I said, the segment, and this is going to be the offset, and this number is, so this is 0, this is 6, and this is 8. So offset is going to be 068 in hex, which is, as we had calculated earlier, 104 in decimal. Okay. So the first 2 bits, so we'll tell which segment register to use. Okay, so now there are 3 segment registers in the memory management unit for the process. So the first two bits are going to tell which segment register to use for these bits for this process using for this address, and bottom 12 bits are going to be the offset. So again, add base plus offset to get physical address. And also check if offset is less than size to find if the access is legal. Okay. So this is the approach that is going to happen. So sorry, just one. So what actually happens is that the hardware masks. So given the address, it first masks with, let's say, 1 1 and rest zeros or zeros, which will be like 3000 in hex, and take AND with this logical AND to get segment, and basically which segment register to use, and then mask with, let's say, 00111 to get offset, which is going to be 0FFF in hex, and again take AND to get offset. So this makes the job easier if the address space is divided like this, that the first two bits represent the logical segment. So if you see that our earlier figure about the address space, you saw that generally when I was drawing earlier, the heap started right after the code. Here we had some free space between that, and the point of doing that so that the heap started at 4 KB, and now the heap starts at 4 KB. So the first two bits of the or the first address is going to be 0 1, all zeros. That's where the heap starts. Okay, so if we have divided the address space into logical segments like this, that makes the job of the register easier, and they can just take like ANDs to get the which segment register to go to and to get the offset. Okay, but there is like some small problems. Is like there are 2 bits and 3 segments. 3 segments. So one segment of address space goes unused. And to solve this, what some OSs do, by having just one bit. and dividing the logical address space into just two parts, which is going to be 0 for code and heap. So code and heap are going to be together, and 1 for the stack. So basically the address space gets divided into like this is 0. So this is where the code and heap will lie. This is 1, where the stack will be there. Okay. Another problem is that each segment, now here also you see that after it getting divided, each segment will be limited to a maximum size because you are using some space now for these things also. Limited to a maximum size. For like in our example, it was 12 bits. So it will give rise to just, so total space was 16 KB. But now because of this segmentation, so this is 00 for code, 01 for heap. This one is not used. Sorry, 10 is not used. And so it got divided into 4 parts, right? So 16 KB got divided into 4 parts, so you get 4 KB, which is also like 2 to the 12. So so this maximum size is there. So you cannot have more than this size of a segment. So the program cannot grow any segment beyond this maximum size. So these are the issues with this approach. And but yeah, today we are going to see this only, and we'll get slightly more into detail about what can be done with this. But so this was the explicit approach, which said that, okay, the first 2 bits of the address are going to determine which segment it belongs to. Sometimes what the like hardware might have is called the implicit approach, where it determines the segment by noticing how the address was generated. So if it is coming from program counter, then it's going to be code segment. If comes off stack pointer, or the address is based off the stack, then stack segment, and anything else is going to be a heap. Okay. So that is the implicit thing, but we'll not be like going into detail for that. Okay, so I said earlier that all the memory, all the examples of the memory accesses that we have seen till now, they are first one was for the code, and the second one was for the heap, right? So what about the stack? So I was like pushing this under the rug till now, and I did not actually like deal with it. That the stack grows negatively. So if you add, I mean, you see, right, that there is a problem. If we add the address of the stack to that, then it's problematic. So what about the stack? But again, like you just do the logical thing and it will be fine. Now to implement that logical thing, you might need some support. Okay. So let's go to the diagram again, or let's see if I can copy it. Okay. Can I copy? Can I just move it? No. Okay. Seems like I can only move it. Okay, let me try once more. No. All right. There might be some way to do this, but I'm not able to find it right now. Thing to save, run nodes. Okay, yes. Seems to work. I just hope it does not move it. Okay. Move down more. And does the earlier thing stay or it has gone? It has gone. All right. Which is something I didn't want to do. Okay. Okay, fine. So let's just go to this diagram and see. I mean, there might be some way to do this, but right now I'm not able to figure it out. So here we see that the stack starts at 28 KB and grows backward, right? So what about the stack? Okay, I keep like shifting towards the right, it seems. So starts at 28 KB and grows. So the problem is grows backwards, right? Grows to 26 KB. This is in physical memory. And in virtual memory, it starts at 16 KB and grows to 14 KB in virtual addresses. Okay. So its size is 2 KB. So now to handle this backward growing thing, so some more hardware support will be needed. And what is this hardware support going to do? 1 bit to indicate whether the segment grows forward or backward. So let's say 1 is going to be forward and 0 is going to be backward. Okay. So now what will the hardware keep? So what will the hardware track? So tracks the following. So segment, the base of that segment, the size, the bounce register. So, and the size is like max is 4K, right? Why? So this limitation is because of the mm, how many bits you have in the address for that segment and whether it grows positive or not. So let's say the code, which was 00, the base of it was 32K, size was 2KB, grows positive, yes. Heap is at 01, this was at 34KB, and size was 3KB. Does this grow positive? Yes. And the stack at 1, this was at 28KB, size 2KB. And does it grow positive? No. Okay. So, but now the hardware should also treat these addresses differently. And what is the way to do that? So, let's say, suppose virtual address of 15KB is the address. So again 15KB, we go back to our diagram. 15KB is going to be somewhere here, right? So, and where we want to address this, we should arrive at somehow 27KB, right? So 15, let's say, so the first two bits are going to be 1, 1, then 1, 1 again, because 15 is 1, and rest are going to be zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, good. So this is now the offset as we had seen earlier, and this is 3KB if you translate this, and this is the segment. Okay, good. So now the offset is 3KB. But of course, if you add 3KB, because the size currently is 2KB, that's going to be illegal. So what you need to do? How do we get the correct offset here? So first we want a negative offset because the base address of the stack is where the stack starts and it grows negatively. So we want a negative offset. So from this, how do we get the negative offset? What do we need to do? How much do we need to subtract? And what is going to be that thing like logically? So this is 15KB, which is actually, if you look at like so from 12KB, this is 3 down, right? So what do you need to subtract to get the correct thing? You need to subtract the logical size of the maximum size of the segment to get there. Okay, so need to subtract maximum size of the segment to extract offset. So how do we do this? 3 kb minus 4 kb is the maximum size of the segment. You get minus 1 kb. And now you add this again to physical address is equal to base. So this is the offset, base plus offset. So this was at 28 kb plus minus 1 kb is equal to 27. Okay. And also now also the bounce check will not check the 3 kb because again that is not correct. So bounce check will always check the final offset that we get after the offset extraction. Okay. If the like absolute value of the extracted offset. Which is 1 kb in this case, is less than the bounce register, which is 2 kb in this case. So it will see it as a legal address, right? So now the hardware also needs to track whether the segment grows positively or negatively. Okay, any questions?
So for this size that we have allocated to the stack, does this contain all the frames that, or it also contains some free space that would be used when like we go into another function? Or is there some way to grow this stack?
Yes, there will be ways to grow the stack, and I'll come to that. So this is job of the OS. So right now I'm just discussing the hardware part. That okay, what is there in the hardware, and the yes, the of course the stack and heap can grow, and the bounce register will usually contain just the current size.
Okay.
I'll come to that in a moment. Okay, so another thing that this allows is yeah, after this, I'll come. Just 5 more minutes. So this allows sharing of data. Okay. So memory segments can be shared across different processes. And like one particular example of this is code sharing, where processes share some code. And again, more hardware support is needed. And in what form this hardware support will be, these are called protection bits. So for every segment, a few bits to indicate whether some other program or some program, any program, can read, write, execute, okay, from this segment. And like, for example, we can set the code to read only, and then it can be shared across different processes, and it will still maintain the isolation. Why? Because the process cannot like change the code. So isolation is there, and also the illusion of the memory space is still maintained. Okay, good. So now after this, the hardware tracks something more. So now there is segment. Let's say there is base, there is size, again max 4K. There is gross positive, and then there is protection bits. So suppose for the code, other things are going to be the same. And then we have here read and execute, no write for the, let's say, heap. So code is 0, 0, 0, 1. Again, the same things. And let's say this is read write and so on. Okay. So again, if some process tries to write into something that it is not supposed to, then the hardware will see that the protection bits are uh, some other way, and it will raise the exception. And if it tries to execute something which is not executable, again the so illegal write execute hardware will raise exception. Okay. So before we go to the OS, there is just one small point is that this way of segmenting is called coarse grained. So coarse grained, what we saw, very few logical segments of big size as in big size as compared to the address space of the process. And what is fine grained? Fine grained is going to be many segments of small size. So some OSs like do that, and what is the hope? That OS can track which segment is in use and keep only that in memory. So the hope is that this will give more flexibility to the OS in terms of memory management. So this is just one more approach, but I'm not going to go into detail of this. Just that, just for you to know that this is not the only way to segment processes address space. There can be more ways where there are like many segments which are there. Okay, so cool. So we have seen till now what the hardware does, and the basic concept of segmentation, that it divides the address space into different segments which can be kept at different places, and the hardware tracks all these segments by using certain registers. Okay. So now there are going to be one pair of base and bounds register per process. Okay. Now what about the OS? So the OS also needs to do more work. For example, in case of context switch, so what it will need to do now in this case, I mean, it's a kind of obvious answer, but still. So when the OS wants to stop one process and run another, what does it need to do now? Like not even slightly different. Yeah, go ahead. Arpit.
It needs to save all these different base and bound register and all this information about the segment.
Yeah. So segment registers must be saved and restored. Okay. Before resuming any process or stopping or resuming. Saved and restored. Anyway, so you can get it from the context that what those should do in case of context switch. All right. So now the question that Arpita was asking, what when a segment grows or shrinks? Okay. So as we have seen, a process might called malloc and then maybe wants to grow its heap or somehow even wants to grow its stack or something. Okay. So suppose it uses malloc. So one way is that it might find space in the current heap itself, but maybe it will not. If not, then the heap segment needs to grow maybe. Okay. So now how will this happen? How will the heap segment grow? So the memory allocation library will use a system call. In this case, it's going to be S break, okay, which will ask the OS to allocate space. So the system will switch to kernel mode. Now the OS will come into play. So then the OS will find more space and update the bounds registers accordingly because now the size has increased. Okay. And then it will inform the memory allocator that it succeeded. And then the memory allocator will allocate space for the object for which the space was asked for. So this is going to be the flow, but there's just one point to note is that maybe the OS will not be able to find space. And this can happen for like, a couple of reasons. First is that maybe no memory is available, or maybe the like heap has already grown to its maximum size. So in that case, the OS will say, okay, I cannot allot any memory, and then the memory allocator would also say, or there will be something bad will happen. Okay, so this is how the growing thing happens. So is that okay, Arpit?
Yes.
Okay, good. Now, another very important task of the OS is to manage the free space. So we have seen that when address space is created, OS needs to find space for the process to run, right? So earlier it was all address spaces were of same size. So OS could see the memory as array of slots. But now that's not the case. Segments of different size. So now the problem that happens is that there can be some small holes at many places. So suppose the OS was till 16 KB, then let's say, so this was 64 KB, and then 8 is unused, 8 is used, 8 is unused, 8 is used, 8 is unused, and 8 is used. So 8, 6, 48, and 16, 64. Okay, good. So this is, let's say, 24, 32, 40, 48, 54. Sorry, what did it? 56, 64. This is 64. Okay, and suppose this was the case that, okay, this was free, this was free, and this was free, and all others were used. And this was the OS, right? So suppose a process now comes asking for 20 KB. So even though free space is 20 KB segment, even though free space now is 24 KB, we have to say no to the process. Why? Because there is nothing contiguous of 20 KB. Everything is of 8 KB. and the segment has to remain together, right? Another problem can be that growing a segment might not be possible because some other segment started just above that or below that. Might not be available. Okay. So again, the OS will reject the request. And to solve this, thing is used, which is called compact memory. I mean, it's not used, but it is a concept. It was used at some point. And this, what it does is rearranges existing segments. So this is like uncompacted. So how will it rearrange? OS would stop any running processes and copy all the data to one contiguous section of memory. So now the memory will look like this. So this is the OS, and then this is going to be half is going to be used. So there will be many segments, one after the other. OS will copy, and the remaining will be empty. Okay. So this was, let's say, 16, and then whatever, 48 or something. 24 is left. Or yeah, 24 was left. So it should be 40. Yeah. Okay. And so it will copy all the data here, all the segments here, and it will save all the registers. But as you can guess, what is the problem with this?
What if a segment had to grow after?
Yeah. And also this is very expensive. Memory intensive, and this is generally also processor intensive because you have to move a lot of things. And also any grow segment request will again you'll again need to rearrange everything. Now you need to shift everything else or like do require a rearrangement again, right? So another approach is the approach of free list, where we just keep track of which locations are available and we keep allocating from that where and how much memory is available, and we keep allocating from that, and we'll see more about this in the next. Okay. So the next lecture is going to be about free space management and how we manage the space, how the OS manages the space. Okay. So any questions about today's lecture? So we are like right on time. So a couple of questions can be there, or anything else. Any questions? So yeah, today we saw the segmentation thing and that how the generalization of the base and bounds approach leads to managing the segment so that internal fragmentation is not there. But still, this thing is there, and this is external fragmentation, that there is this small chunks of memory which is unused. So this is, and this will see how to take care of this in next lecture. So yeah, any questions about anything? Okay. If not, then thank you all for coming and see you on Thursday.